Earth Science Time. Today we are talking about Earth's history again. This time we're talking about a little bit later of Earth's history. Let's title this the Phanerozoic Eon. The Phanerozoic Eon. Do you have your little chart? That's my first question. Usually the first question is, what do these words mean? But this time, do you have your little chart is the first question. If you have your little chart, please get it out in addition to your notes. Oh, and someone remind me to write down the objective. I've been forgetting that lately.
I'm just going to write down the objective.
Thank you. So if you have your little chart, I'll put this one on the camera so that if someone watching it, possibly Eli, doesn't have it, they could pause it on that frame and we can look together. Okay, so you can see, if you have the same one as I do, there are two different ones that I handed out, but this one that says International Chronostratigraphy Chart would probably be the better for this, because I believe that 2009 USGS one does not have the word Phanerozoic on it at all. I could be wrong, but I don't think it does. Does anyone? Which one do you have, Will?
I can't find it at the moment.
Well, after I'm done pointing at it, you can use mine, or you can have mine even, and we'll make copies later. But you see, when we have this eonothem here on the where these columns are labeled, eonothem means the time, right? Them, from the Greek for time, of an eon, and then we have an erothem, and then a system, which is also called a period, and then we get down into what are sometimes called epochs or ages. But you can see that for this first part, what we talked about last time was really this little red chart here, and that was called, it is not officially called the Precambrian, but that group of eons is called the Precambrian. Some people say Precambrian. And you can see for the rest of them, the other three columns, what is the eonothem, or the eon? It's light blue on each of those three columns to the left. Phanerozoic. So that's what we're talking about. So we're talking about these three eons here. What are they? Let's list them in order. That's the first thing we're going to do, because, like I say, it's not actually super important what this word means. It roughly means whole life, or complete life. Maybe zoos from the Greek for life, specifically animal. But so this Phanerozoic roughly means complete life. That's not really what's super important. If that helps you remember it in some strange way, like it helps me remember it in some strange way, that's fine. But really, just memorizing this word as rote of the eon that encapsulates the following eras. The eras within it are, let's say them. So what, the oldest one, what do we call that one? And you can see on your chart. I'm not expecting you just to make these words up. Nope, that's a period. We're looking at the eras, or that chart labels them, because it's international, labels them erotherm, or erothem. Paleozoic. Okay, so let's list these, and these you will have to have memorized in order. Paleozoic, what's the next one? Mesozoic, and just so that I know that you are also finding these things, Will, what's the last one? Or I shouldn't say last, maybe the most recent one, the current one.
Cenozoic.
Cenozoic. Good. Looking at these prefixes here, again, we see this zoic relating to what? Life, yeah. So you can tell what's kind of important as scientists have chosen to break up these groups of time. What's important to the scientists are really two things, and that actually relates to the objective, which, thank you for reminding me to write it down. The objective is, there are two main things that we focus on, and they're both in the objective as we go through Earth's past. The objective reads, William?
Model biological and geological changes during the Earth's history.
This is almost illegible because it's still wet as I'm writing it. Model biological and geological changes. What was the rest? I'm sorry.
During the Earth's history.
During the Earth's history. So the modeling, to a large extent, you have already done. That's what you did in the lab. And we're going to relate this to that here in a second. But did you model, just as a yes or no question, did you model biological changes? Yeah. I would say yeah. Well, a specific one. You didn't model all of them, but that would be very difficult. Did you model geological changes? Yeah. So you did do this. I need to stop saying That's really driving, my own voice is driving me crazy when I say I shouldn't say better because I like this objective and I think it's important that you model these things. But to what we're talking about in the discussion today, a better way for this to be phrased is to relate the biological and geological changes. So you might, in your own thing, I'm not going to change it on here, but you might also put /relate after model because I do want to relate the biological, and that gets back to our little word here. What does this zoos mean? Or zoic is how it shows up in this word, but the Greek root is zoos. Life, yeah. Remember, and we had said bios or bios, biology. At the beginning of the year, the biosphere, remember, that was life. In the Greek, and as it's used in the Greek roots in modern science, zoos usually specifically refers to animal life, but in this context it means life. And so now we have these other prefixes here. Paleo, Meso, and you said Ceno, which is totally acceptable. I always say Ceno. Don't trick yourself into thinking, stop saying don't trick yourself into thinking that when I say Ceno and you say Ceno that I'm saying that you're wrong. There are two different ways of pronouncing it, okay? So, paleo, can you guess what that might mean? Would it have something? I like that. It isn't quite right, but I like that good guess because you're recognizing that they are in order from oldest to most recent. And really, the true geologist would be frustrated with me for organizing this way because the true geologist, like the person who wrote that, I don't have mine anymore, but the person who wrote this timescale trusts and knows and shows that the oldest things are at the bottom. Remember, we talked about superposition. So really, if I was a good geologist, I would have listed those from the bottom up. But anyway, paleo does not mean first in the strictest sense. What could you guess again? Let me give you a hint. What might the paleontology, the study of paleo, be? Have you heard of paleontology?
A little bit. Would it be the study of a rock with pale in it, I guess?
No. Paleontology is a study of ancient organisms. Paleo means ancient or old or oldest. I keep using several words because none of those is exactly right, and so I'm just saying a lot of them so that we can kind of orbit the true meaning. So ancient. Meso, you could probably guess what meso means. If you've taken anything of med terms, you'll know this one. No, you haven't taken med terms? Okay, I'll just tell you because I'm middle. And then now maybe you can guess what Ceno means. Yeah, I like that. I even said that, and you might be right. You're not right that it means that, but this might be the last Zoic. Recent is usually what we agree on. The little sin in this recent, that's a Latinate word actually, but it has the same, it's related to the Cen in Cenozoic or Cenozoic. So we have ancient life, middle life, and recent life. What is the dividing line? Like what do you think is going on your chart? I want to hold up mine, but I don't have one anymore because I had to give mine to Will because he lost his. What do you think is the dividing line here? Do they seem like, looking at the ages, the actual numerical ages, which, by the way, what's the evidence for those actual numerical ages, just so that we're all on the same page? Like, what evidence exists that those ages, you see that there's numbers here, what evidence exists that is correct? Or that fossil record, there are more, what else? Rock record, and one more very big one for the fact that they're numbers. What would give us actual numbers? I mean, with those two things you said, we could fairly definitively say the biological progression or even which things are older, but how do we get these actual numerical ages? It doesn't work like human history, where we can just kind of like look and see like, oh, this writing took place over 100 years, because there wasn't writing, it's prehistory, that's the whole point. So how do we get these numbers? You might remember from a couple lessons ago. How do we find the actual age in years as a number of radiometric dating? That's what we're getting at, yeah. So the evidence is radiometric dating suggests these. And so looking at, for instance, the Paleozoic and the Mesozoic. Where do you see, and by the way, this chart is written from right to left and bottom to top, so good luck. But approximately how long did the Paleozoic last? So where does it begin? I'm sorry, by where I mean when. So we're looking for the bottom of the rightmost column of the Phanerozoic. Where does the Paleozoic begin? And again, I mean when. So about 541 mega annum to, when does it end? 251 mega annum. Okay. What about the Mesozoic? From about 251 mega annum, about 66 mega annum, and then the Cenozoic from about. Good. I've written exactly that. Remind me, William, what does mega annum mean?
It means million years.
Million years. Good. Approximately, just do some rough math. How long did this one last, the Paleozoic? About 300 million years. This one? About 200 million years. This one? We don't know yet. We'll find out very soon, it seems like. Stop saying 66 million years. And so are they a certain length of time? Can we correlate? Could we do a unit conversion for 1 eon is 100 million years? Could we do a unit conversion for 1 eon is 100 million years? No. Why not? They're not. So what is the dividing line? It's not like an eon is a certain amount of time, like an hour is, or an eon is a certain amount of time, like a week is. What is the dividing line between these eons? If you had to guess, which I'm forcing you to guess, I'll give you a little hint. It relates to the objective. What kind of changes, that's a good way to phrase it, between your hint and this new question, what kind of changes might divide, at least in the mind of geologists, biological and geological changes? So what might be some big biological changes that might cause it that when we look back through the fossil record, scientists are comfortable saying things are different enough that we can categorize this in a whole separate category. What kind of big biological changes might happen?
People actually start thinking.
That ain't one of them. Somewhere in here. Yeah, that would be one. That's not one that we actually, to my knowledge, that we use. That is a biological change. But I think you're getting trapped in thinking of one, anthropocentrism, where human beings are the most important. Didn't exist for almost all of this. And two, that it's about one specific species, because it isn't. And that's the key. What major biological change could happen to a lot of species at once that we can see in the fossil record?
From being stuck in the ocean to going to land.
Okay, I'm going to, that is not correct, but I'm going to count it. I think you're getting at the exact right thing. So from I forgot to say that back here we had the Precambrian, which is again not an eon. If we had to say an eon, we would say the Proterozoic eon. And the Precambrian was from about 4.6 gigaannum to 541 megaannum. So that one, again, not an eon, but the rest of the time we talked about last time, was about 4 billion years. Excuse me. So the major change here, actually, this is what we talked about last time, the Cambrian explosion. So what Will said is things moving from the water onto land. That did not happen at this time, but what you're getting at is a rapid diversification of life. Diversification meaning lots of different critters are evolving. Rapidly means over a relatively brief geological time, so less than, I don't know, some number of million years as opposed to a very long time. So this one, between the Proterozoic eon and the Paleozoic era of the Phanerozoic eon, what the fossil record shows is this Cambrian explosion, where before there were only very few multicellular organisms and they were relatively simple, and then within a very short geological time, almost all of the phyla that we have today, a rapid diversification of life. Okay, now let's get to these two. These two are both a similar thing. I hope there's an announcement. Hey, good thing we have a video of this, because now I'm just going to be talking to Eli, and so it's good that Eli's taking notes, and you guys will have this video to watch after a little while. Okay. It's going to make it a little bit less of a discussion and more of me and Eli just hanging out, but that's okay. So watch this video. This will be on Google Classroom. We're still having class, Cody. Okay. Watch this video on Google Classroom, okay? Okay, so the dividing line here, besides things lots of new things becoming alive, Eli. What other major thing could happen? Lots of new things coming alive, lots of things dying. There you go. Death is these other two little dividing lines. To the end of mass extinctions. Would you please take notes over this, Eli? So mass extinction, do you need a piece of paper? Let's use one of these lab forms because that's what I have handy. You write down your notes on it, okay? Thank you. Okay, so these two are both mass extinctions. This one, the one from the Paleozoic to the Mesozoic, is called the end Permian extinction event. And that was about 251 megaannum, but it lasted millions of years, and so we could really say around 250 megaannum. And what happened here, it seems, evidence suggests, rock evidence, rocks all over the world show this, ash layer, and some of them even show the actual lava flow itself. And fossil evidence, that is that about 99% of living things died within the fossil record shows us that it was probably a major volcanic event that both destroyed all the life around it. So here's my map. What is today eastern Russia, all over this area we find basalt deposits that are of this age, radiometric dated, and they provide evidence of an ancient lava flow. And so it seems that around this time, 250 million years ago, in this area, a supervolcano or something like a supervolcano erupted. And not only was this area on lava fire for about 5 million years, maybe even longer, maybe even up to 50 million years, but also totally changed the chemical nature of the ocean because of the effluents, because of the output of those volcanoes. So we have a major volcanic event, lots of volcanic eruptions all over, I would say roughly between a quarter and a half of Earth's land surface was probably actively on fire. And to further add to that fire, to literally add fuel to that fire, during the Paleozoic there was this, and this will be like a little side note, I'll have a little side note box here. During the Paleozoic there was a time of coal production, coal swamps in the what's called the Carboniferous, which literally means coal-bearing, which we can find from about 350 to about 300. During this time, plants had evolved the ability to become strong and upright on land due to cellulose, due to sugar molecules combining to form cellulose. And when they died, much like plastic today, do you know, Eli, that if you throw a plastic bottle out the window of your car, which you should not do, what's going to happen to it? If you come back a year later, what's it going to look like?
It's going to look crumpled up.
Crumpled up, but it's still going to be there, right? If you come back in 10 years, probably still there, unless, the wind blew it away or a trucker came and got it or whatever, coyote. If everything else stays the same, 100 years from now, maybe we think even 1,000 years from now, that bottle will still be there because it's non-biodegradable. Have you heard that word? That's how cellulose was during this time. So the cellulose that had developed in plants, or I shouldn't say no, but fossil evidence suggests that much later, bacteria and fungi developed the ability to digest cellulose. And so when a plant would die, it would just stay, it would just fall, and these massive piles of cellulose would eventually degrade into carbon. And that's where all the coal we have today comes from this time, because now when a tree or a plant dies, the bacteria and the fungi just eat it. But at this time, it would just pile up. And so that adds fuel to this fire. And now the whole world's on fire, and the atmosphere changes, and most things die, the fossil record says. This other extinction event, I'm going to do a chaotic arrow here. This other extinction event is called the KT, or Cretaceous, which actually starts with the letter C, but in German it doesn't. Cretaceous Tertiary, which again, we do not even use that terminology anymore, but we still call it KT, extinction event. You might have heard this at one. Do you know how the dinosaurs died?
Yeah.
How?
They
What hit planet Earth? you remember? You've
A
probably,
fallen rock.
yeah, a meteor.
I mean,
Evidence suggests, and the evidence for this is that in the same way that all over the world we see evidence of this at 250 million years ago, we see evidence of this volcanic eruption. All over the world we see it at approximately 66 megaonnum. All over the world we see this layer of iridium, which is an element on the periodic table that is fairly rare in Earth's crust, but appears to be abundant in the asteroid belt. And so all over the world we see this iridium layer is the evidence. And it's strongest around the equator in the Western Hemisphere. And in fact, we think, evidence suggests, that this area of the Yucatan Peninsula, there's an impact crater, which was probably where an asteroid or something from the asteroid belt, a meteor from the asteroid belt, impacted Earth. And with enough force that the atmosphere was changed. The atmosphere was probably about 900 degrees Fahrenheit for a period of almost a month. And so almost everything above ground on land and many things in the sea died. And we have this evidence all over the world, and so we use this as a marker for the difference between these two ages. Now within these ages, so those are the dividing lines. And then, by the way, the dividing lines of these individual periods and then even down to, eras and then periods and then even down to ages, we use similar things. It's not always an extinction event, but it's something clearly shown in the fossil or rock record. They are not certain lengths of time. They're divided by things in the fossil or rock record. Within these time periods, I'm just going to rewrite these all down here again. Paleozoic, Mesozoic, and Cenozoic. There's a lot of other things going on, which many of those we will learn specifically from that video, but you should know that the Mesozoic is usually considered the age of dinosaurs, what we might call the dominant or the most influential on their environment organisms during the Mesozoic are the dinosaurs. And in the Cenozoic, we call this the age of mammals. We're mammals, right? We've got hair. We're endothermic, meaning we produce our own body heat. We don't all produce milk for our young, but we all have the apparatus for that. These are the defining characteristics of a mammal, and it seems, at least to scientists, that the primary organisms that influence their environment in this age, in this time, is the age of mammals. And by the way, in the Paleozoic, we had several different ones. We had the age of fishes, the age of arthropods, and the age of reptiles are the ones that I have heard. I'm sure there are others. You might even include an age of amphibians in here, but usually we consider the age of fishes to be the Cambrian, Ordovician, and Silurian. The age of arthropods would probably be including also the Silurian, Devonian. I would be hesitant to put Carboniferous on there, but then the Permian is the age of reptiles. And you can see kind of the progression of evolution throughout this. And that's another thing that the video primarily focuses on, is the biological changes. And going along with the biological changes, these are obviously biological terms, but we also recognize, I'll put this also in the side note box, that each of these has its own kind of associated famous mountain building episode, where mountains are continually built due to plate tectonics on Earth. But it just so happens that they kind of line up with these two. In the Paleozoic, we see the Appalachian Mountains formed. Appalachian Mountains formed. In the Mesozoic, we see the Rockies. And in the Cenozoic, we are seeing the Himalayas form. And there are other mountains, like there's the Atlas Mountains and the Alps, and those go in these columns too. But the ones that your book describes most in depth, the ones that the video talks about the most, and the ones that are on the test are these three major mountain ranges. And do you know these mountain ranges? You know the Rocky Mountains probably, at least. Have you heard of the Himalayas? And have you heard of the Appalachians? So I'm going to show you on the map here that you know where the Rocky Mountains are. They go from somewhere in northern Canada. This, by the way, the mountain building episode that caused this is called the Cordilleran, and it goes all the way down, then it becomes the Andes here, but it seems like it was probably the same or a similar mountain building episode that caused this whole spine of North and South America. And the Himalayas are here, where Mount Everest is. Have you heard of Mount Everest? What's true of Mount Everest? What do you know about Mount Everest? Say it. You were about to say it.
What?
You were about to say it. What's Mount Everest? It's a mountain, yeah. It's the tallest mountain. Did you know that? It's the tallest mountain. And the Himalayas, because they are the most recent mountain range to form, they formed in the Cenozoic. Some of them, they're still forming in the Cenozoic, are also the tallest because erosion has worked on them the least. The Rocky Mountains are not as tall, but still fairly tall because erosion has been working on them for about 65 million years. And the Appalachians here, which you can tell just from even from the map, and actually they go up into Scotland too, are not very tall, and that's because erosion has been working on them the longest. They grew, we might even say, in the Paleozoic. So there are these geological changes, which the ones I've talked about are called orogenies, which means mountain building. There are other geological changes, like the formation of supercontinents, like Rodinia and Gondwana and Pangaea, and those are discussed in the video. The way that the continents move, we have evidence for based on fossil and rock evidence. So there's geological changes. There are these biological changes. And there are also changes of both that relate both. For instance, if I bring this map down again, when we find fossils of dinosaurs, we very frequently find, I even have it marked on this map, we find fossils in a range, not just of dinosaurs, but Mesozoic plants. We find fossils of the same kind in this range and this range. And that tells us, so this is both a biological change, right? Those creatures evolved. And it's also a geological change because now these are separated by the ocean. And things like land plants and land animals that could not swim thousands of miles, we find fossils of them in the same area. And so we use those changes together to tell us about Earth's past. Now, as I said, the details, the finer details of like what kind of creatures there were and what kind of geology changes were going on, we'll primarily watch from that video. But this is I would call this a fairly broad and certainly not exhaustive, but at least a good start, a good survey of the way that we look at the Paleozoic, Mesozoic, and Cenozoic, which together form the Phanerozoic eon. Do you have questions? Okay.